Ever get that feeling like the more you learn about something, the weirder it gets?
Yeah, I know how that feeling.
It's like you peel back one layer of the onion and there's a whole new level of strange underneath.
Definitely.
And nowhere is that truer than in quantum mechanics, right?
Absolutely.
I mean, we're talking about the very building blocks of the universe here. And even the geniuses who were laying down the groundwork, well, let's just say they didn't always see eye to eye.
It's true. And these weren't just like polite disagreements over equations. They were grappling with the very nature of reality itself.
Exactly. And today, we're diving into the deep end with Erwin Schrödinger. Now, he had some serious issues with the direction quantum mechanics was taking, and he wasn't afraid to shake things up a bit.
And knowing your thirst for understanding the why behind things, I think you'll appreciate where Schrödinger is coming from.
Oh, absolutely. He was one of those minds that wasn't satisfied with just equations and probabilities. He wanted a clear picture of what was really going on at the quantum level. So we're digging into the speech he gave in 1952 called The Meaning of Wave Mechanics. It's pure Schrödinger, full of skepticism and bold ideas. You ready for this?
Let's do it. This speech is a fascinating window into the debates happening at the very heart of quantum physics.
All right, so context time. In the 1920s, Schrödinger made a huge splash with his famous wave equation.
Right, which basically revolutionized atomic physics.
Totally. It seemed like the perfect tool for describing the behavior of atoms. But there was a catch, wasn't there?
There was. You see, while everyone loved the elegance of Schrödinger's equation, a different interpretation of quantum mechanics was gaining traction. Probability interpretation.
Yeah.
And Schrödinger was not a fan.
Not a fan at all. And, I get it. It's like you have this beautifully descriptive equation that explains how these waves behave, but then you're told, oh, but we can't actually know anything for sure until we measure it. And even then, it's all probabilities and chance. It's enough to make your head spin.
It's understandable why some physicists, including Schrödinger, felt like something was missing. They wanted a theory that described reality itself, not just our uncertain observations of it.
Okay, so before we jump into Schrödinger's full-on rebellion against the probability party line, can you give us a quick and painless explanation of what this probability interpretation actually is? No PhDs required here, just plain English, please.
Think of it this way. Imagine flipping a coin.
Okay, got it.
Before it lands, it could be heads or tails, right? The probability interpretation says that quantum particles, like electrons, are kind of like that coin in midair. They exist in this fuzzy state of being both possibilities until we actually measure them.
And the very act of measuring forces them to choose a state, like the coin finally landing on heads or tails.
Exactly. And the wildest part is that it's not just that we didn't know which state it was in before measuring it. The act of observation itself somehow forces the particle to take on a definite state.
Okay, see, that's what I'm talking about. Even I'm getting a little mind blown here, and I'm just a curious dude with a microphone. So Schrödinger, with his love for elegance and a deep understanding of waves, he wasn't buying it.
Nope, not one bit. He had 4 major issues, which he called difficulties, with this whole probability-driven view of quantum mechanics. And he spells them out in this speech.
And you've got to admire his directness. There's this one part where he basically says, look, I'm not holding back here. I'm fundamentally opposed to pretty much everything quantum physics has become over the last 25 years.
He held nothing back, that's for sure. He felt very strongly that something fundamental was missing from the way everyone else was interpreting quantum mechanics.
So what was his first big difficulty? What was he struggling to reconcile?
Well, for one, he couldn't quite wrap his head around this idea of a particle, like an electron, being described as a wave packet that just constantly spreads out over time.
Right, like a ripple in a pond.
Exactly. It seemed counterintuitive to everything he knew about how the world worked.
It does make your brain hurt a bit. I mean, if particles are spreading out like ripples on a pond, how can we ever say they have a definite location? It's like trying to nail jelly to a wall.
Exactly. It just didn't sit right with him. And that was just the first of his concerns.
Okay, I'm hooked. Lay the next difficulty on me.
So Schrödinger's second issue had to do with the wave mechanical model of the hydrogen atom. You know, that classic picture of an electron buzzing around the nucleus.
Right, like a tiny little solar system. We've all seen that diagram.
Exactly. Well, Schrödinger spotted what he felt was an inconsistency in how that model was being used. See, the electron, as a cloud, would partially shield the positive charge of the nucleus.
Makes sense. The electron cloud would kind of balance out the positive pull of the nucleus, right?
You'd think so. But here's the thing. When physicists were busy calculating the shape of that electron cloud, they were only factoring in the pull of the nucleus, not the fact that the electron cloud itself would also create its own electric field.
So it's like they were forgetting to account for half the forces at play.
Precisely. And that kind of oversight drove Schrödinger nuts. It felt like a cheat to make the math work out, and it made the model feel incomplete.
Yeah, you can't just ignore part of the system and expect to get a truly accurate picture. It's like trying to bake a cake but only using half the ingredients. You might end up with something, but it's not going to be pretty.
A perfect analogy. And this actually gets to the heart of why Schrödinger was so bothered by the whole probability interpretation thing. He felt like it was letting physicists off the hook by saying, oh, it's all just chance and uncertainty anyway, instead of digging deeper to find a more complete and consistent explanation.
Okay, that makes sense. He wasn't just being difficult for the sake of it. He genuinely felt like something was off about the whole approach. All right, what was his third big hang-up?
This one's a bit of a head-scratcher, but it gets to the core of what makes quantum mechanics so strange. It has to do with the idea that energy isn't continuous, but comes in these little packets called quanta.
Right, like the universe has a cosmic vending machine that only takes dollar bills, no coins.
Exactly. And what bothered Schrödinger was this. His wave equation naturally described things in a smooth, continuous way, like a flowing river. But experimental results, like Planck's radiation law, kept suggesting these abrupt jumps between energy levels, these quantum leaps.
So it's like trying to fit a square peg into a round hole. The wave equation describes smooth, continuous change, but the experiments kept showing these jerky, quantized jumps.
Exactly. And to make sense of these jumps, physicists had to say, well, the wave function doesn't actually describe the physical reality of the particle. It just tells us the probabilities of finding it at different states when we make a measurement.
So instead of the wave function being like a direct representation of reality, it was demoted to a probability cloud. No wonder Schrödinger wasn't thrilled.
Exactly. He felt that a fundamental theory of physics should be about what was really going on, regardless of our limited ability to measure it, and relying on probabilities felt like admitting defeat.
It's like saying, we don't know where the electron is, so let's just draw a fuzzy cloud and call it a day. Not very satisfying, is it?
Not for Schrödinger. He wanted a theory that offered a clearer picture, one where the math pointed to a deeper reality. Which brings us to his fourth and final difficulty, and this one might be the most puzzling of all.
Hit me with it. I'm ready for anything at this point.
This one dives into the strange world where light acts like a particle. Remember the photoelectric effect, where shining light on a metal can knock loose electrons?
Vaguely. It's been a while since high school physics. Remind me what's so weird about that.
The weird part is that it only works if the light is above a certain frequency, like it's delivering energy in these little bullet-like packets, or what we call photons. This suggested that even light, which we normally think of as a wave, could sometimes act like a particle.
Hold on, so are we saying light is a wave or a particle? My brain can't handle both.
Right. It's one of those quantum mysteries that make you question everything you thought you knew. But the point is, this particle-like behavior of light didn't fit with Schrödinger's vision of a wave-centric reality.
It's like suddenly discovering that the ocean is made of tiny little water droplets instead of these vast interconnected waves. It throws a wrench into everything.
Exactly. And it made it harder to dismiss those particle-based interpretations of quantum mechanics that Schrödinger found so dissatisfying.
So we've got Schrödinger, wave equation in hand, standing defiant against this tidal wave of probability and uncertainty. He's laid out his four big issues. But he doesn't stop there, does he?
Oh, no. Schrödinger wasn't just about poking holes in other people's ideas. He was a firm believer in finding solutions. He had a couple of radical ideas of his own up his sleeve, based on some pretty wild new ways of thinking about quantum mechanics.
Okay, now we're talking. I knew there had to be more to the story. But we'll have to take a quick break before we dive into Schrödinger's counter-arguments. Don't go anywhere. Things are about to get really interesting. All right, so we left off with Schrödinger basically saying, hold on, everybody, I've got some thoughts.
He wasn't messing around. This was a big deal. Schrödinger was going up against the established view.
Right, and he's not just griping about it. He's got his own ideas, right?
Exactly. And these were really radical, really wild ideas for their time.
Yeah.
He wanted to fundamentally change how people thought about quantum mechanics.
So spill it. What were these radical ideas? Give me the inside scoop.
Okay, so his first big idea was this. We got to abandon this whole idea of particles like electrons behaving like, tiny little billiard balls bouncing around.
Okay, so no more picturing electrons as these little spheres with a minus sign zipping around a nucleus.
Not really. Schrödinger wanted everyone to shift their perspective. He was pushing for a picture where the wave aspect, that was a fundamental reality.
Whoa.
Those particle-like properties that we sometimes observe, those were more like fleeting ripples on the surface of a pond, you know.
So the particles aren't really things. They're like these passing manifestations of a deeper wave reality.
Yeah, you got it. You're getting it. That's a great way to put it. And his second big idea, it kind of built on this whole concept. It's something called second quantization.
Second quantization. That sounds intimidating.
It does sound like it, but stick with me. Imagine the ocean, right? Waves are crashing, the tides are rolling in. Now imagine instead of waves of water, it's this vast, dynamic sea of possibilities, and particles in this picture, they're like these fleeting crests of those waves, momentarily appearing as those possibilities interact and interfere.
Hold on. So particles aren't little balls of something that have waves associated with them. The particles are the waves, or at least expressions of them.
Exactly. Yeah, that's it. It's like the difference between looking at a single wave in the ocean versus understanding the ocean as this interconnected system of energy and flow. Schrödinger, he really believed that this ocean of possibilities view, it was crucial for truly understanding the quantum world.
Oh, okay, that's a really cool way to think about it. So armed with these two big ideas, no more individual particles and this whole second quantization thing, how did Schrödinger go back and address those four difficulties he had with the standard interpretation?
Let's take that first issue, about those pesky wave packets spreading out.
Right.
If we let go of this idea that the wave packet represents one specific particle, the spreading, it's not a problem anymore.
It's not like the electron is dissolving into the void. It's more like that wave of possibility, that ocean we were talking about. It's just evolving and changing over time.
Exactly. Yeah, you got it. And Schrödinger's wave equation, it's beautifully equipped to describe that evolution.
Okay, that's actually surprisingly intuitive. What about his second issue, the inconsistency with the hydrogen atom model? How did he address that one?
Well, that's where second quantization really comes in handy. It provides a much more rigorous framework for dealing with these systems of multiple particles. You just can't look at each electron in isolation.
So it's like they were trying to solve this giant Sudoku puzzle by only focusing on one square at a time. You need to look at the whole picture, right?
Yeah, you got it. Second quantization gives you the mathematical tools to account for the interactions between all those particles and the fields they create in a much more complete and consistent way.
Okay, so more complex math, but ultimately a more accurate view of reality. All right, what about that third difficulty? The whole energy coming in quanta business. That one always throws me for a loop.
Right, the whole quantum leap idea.
Yeah.
Well, Schrödinger, he argued that maybe, just maybe, we don't need to accept those jumps between discrete energy levels as, actually happening in reality.
Wait, really? But what about all the experimental evidence that suggests energy is quantized? Those distinct energy levels in atoms and all that.
Right, so here's the crux of Schrödinger's argument. Just because our instruments give us discrete results, it doesn't necessarily mean the underlying reality is also discrete.
So it's like our instruments are kind of forcing us to see a pixelated version of reality, even though reality itself might be perfectly smooth.
You got it. That's a great analogy. It's like trying to measure the circumference of a perfectly round ball using only a ruler with centimeter markings. You'll get a whole number of centimeters, right?
Mm-hmm.
But the actual circumference is likely something much more precise with decimals and all that.
That makes sense. Our instruments are kind of limiting our view, making us see things as quantized, even if maybe they're not. Okay, that's kind of mind-blowing. But what about that last difficulty, the one where light acts like a particle in the photoelectric effect? How did Schrödinger reconcile that with his whole wave-centric view?
Well, he believed that the wave aspect was still crucial, even in phenomena like the photoelectric effect. He suggested the apparent, particle-like behavior of light. It was a consequence of how those light waves were interacting with the electrons in the metal.
So it's not that light suddenly morphs into these tiny bullets of energy. It's more about how the waves are interacting with matter.
Precisely. Think of it like pushing someone on a swing. You only get those big noticeable increases in energy transfer when you push it just the right moment, at the swing's resonant frequency. The same principle. It kind of applies to light interacting with electrons.
Wow. I am starting to see the universe in a whole new light.
Mm-hmm.
So Schrödinger was basically saying, don't throw out the wave just yet. We can explain all this weird quantum stuff without resorting to particles and probabilities as the fundamental truth.
Exactly. And He went even further to argue that while the probability interpretation might be logically consistent, it actually lets physicists off the hook too easily.
Now that's a twist. I thought consistency was a good thing in science.
It usually is. It usually is. But Schrödinger felt it allowed physicists to avoid tackling this very fundamental problem, the connection between the really elegant mathematics and the, let's face it, often messy reality of experiments.
So it's like having a perfect recipe for a cake, but no instructions on how to actually bake it. You might end up with a total disaster, even though the recipe itself is flawless.
A perfect analogy again. Schrödinger wanted a theory that didn't just tell you the probability for finding an electron somewhere, but also actually explained how our kind of clumsy measuring devices interacted with that wave-like reality.
He really was ahead of his time in so many ways. So while he might not have had all the answers, he definitely raised some really big questions about the nature of reality itself. And it kind of makes you wonder, is there a more elegant wave-based picture of the universe out there just waiting to be discovered?
That's the beauty of science. Every answer leads to more questions, deeper mysteries to unravel. And Schrödinger's insights, they continue to inspire physicists today to keep searching for that deeper picture.
It's enough to make you want to grab a physics textbook and, dive headfirst into the quantum abyss. Thanks for taking this mind-bending journey with us. Until next time, keep those brainwaves flowing.